BKW Physics. I'm Mr. McConley, and today we're continuing our talk about modern physics. And we started with a quick review of the Bohr model, where the nucleus is in the middle, consisting of protons and neutrons. We have electrons and orbitals around the outside. And if you're in the closest orbital, it's the ground state, and as you move away, those are called excited states. Now that leads us to, well, if an electron is changing energy levels, how's that going to work? So you need to be in your reference table. Page 3 is the way it's labeled. It says energy level diagrams, and you see that there's hydrogen and mercury energy level diagrams. Along with that, if you could be flipping between that and page 5 under modern physics, we're going to spend time right now talking about the equation which is on the second line of modern physics, which says the energy of a photon, just as a quick reminder, photon meant light. So energy of a photon is equal to the initial energy level minus the final energy level. EI minus EF. That's directly from your reference table. Now that in itself is just an easy equation in terms of what you guys have been exposed to at this point, because all you have to do is, if you know the initial energy level, you know the final, you just subtract them, done. Easy. But there's a few things that are a little bit weird about this. First of all, when you go to your reference table, you'll note that the energies are in units of electron volts. And electron volts work fine for this, except when you go to apply this information, once you subtract, and then you want to apply it to, let's say, another energy of a photon equation, like HF, and this one we did the other day. So if you want to apply it to that equation, when you put it into this equation, it needs to be in units of joules. This needs to be in joules. This one can be in joules, or it can be in electron volts. So what I'm implying is, if you do electron volts that you get from your reference table, you're going to have to convert it to joules. So let's look at the conversion. So, Kyle, if you can take a look in the front of the reference table, front page, and tell me what the conversion is between electron volts and joules, I'd appreciate it.
Electron volt is 1.6.
1 electron volt is 1.6 E negative 19 joules. Okay? This right here, front page, will allow you to switch between what you get here and what you need for this equation. Okay. So that's concept's pretty easy. Let's do an example. So out of the textbook, this is a problem 30 in our textbook. Go ahead and read that.
Determine the frequency and wavelength of the photon emitted when an electron drops from N3 to N2 in an excited hydrogen atom.
We're going from N3 to N2 in hydrogen. Okay. So it looks like we're doing an energy change. So we're going to start with the change in energy of a photon is E initial minus E final. And now I want you to look up and see if you can read off of the chart, what is the energy for hydrogen? For N3 in hydrogen, see if you can figure out what that energy actually is. Someone in the back row here. Find a number for me. Take a look at the reference table. Look at N3. Find me a number. Yeah. Negative 1.51. And what are the units on all of these? See, that's why I was giving you that conversion. That's going to be inconvenient. Minus, and what is the number associated with the N2 level?
Negative 3.4.
Negative 3.40 electron volts. So doing a little quick math here, get your calculators out so you can follow along. Doing a little quick math, you subtract, and since this is a minus minus, you're going to treat it like a plus. Anyhow, you're going to get 1.89. Check that, make sure I'm right. You agree? Okay. But they didn't ask for that. They asked for the frequency and the wavelength, and I didn't get either one. I got the change in energy, but I needed to start there so that I could move forward. So what I want to do next is, in order to find frequency, I'm going to base my solution on the idea that the energy of a photon is h times f. Because then all I have to do is take the energy and divide it by Planck's constant when I rearrange the equation. I have the energy. I have it right here. This is the energy. Only problem with it is it's in the wrong units. So we got to do a little conversion and we got to make it into the right units. So let's do that first off. Let's take 1.89 EVs and let's apply what Kyle found on the front of the reference table a little while ago, which is that 1 EV is 1.6 e negative 19 joules. Notice I put the EVs on the bottom so they would cancel, so you're basically just multiplying those two together. And what do we get when we do a little conversion there?
.024 e negative
3.024 e negative 19. I agree, that's what I also got when I checked it earlier. So now we have, this is the energy. It's the same as this number, it's just in a different unit. Okay, those two are the same. So let's plug them right in. We got 3.024 e negative 19 joules over, yeah, I don't have Planck's constant memorized, so I got to go to the front of my reference table. I go and check that out, and what do we find on the front of our reference table?
6.63 e negative 34 joules per
E negative 34, and what are those units again, Cheyenne?
joules times seconds.
Joules times seconds. Well, the numbers are getting awkward, but nothing your calculator can't handle. So, what do we got? Anyone confirm that number? 4.56 E14? Confirmed? Confirmed. Very good. Now, I just threw the unit of hertz on there. I didn't really say anything. Hertz. Where did I get that from? Well, if I back up and I don't write hertz, I mean, I knew it was hertz because it's a frequency and I know frequency are in hertz. But really what I got is I got joules over joules per second. So the joules would cancel and leave you with 1 over seconds. And if you recall back to a while ago when we did waves, 1 over second was the same as hertz. So that's why I could jump to that unit of hertz. So the frequency is right there, 4.56 E14 hertz. And what you could also do at this point, as to kind of tie in some other things, is you could go to your page 2 of your reference table, the electromagnetic spectrum, and you could look and see where 4.56 E14 falls. So if we look at our frequencies, E14, that is definitely in the visible spectrum, and we're at 4.56. So 4.56 is what color?
It's red.
We're in red. This is red. Right there, what we found is we're talking about red. Okay, great. But that's not all they asked for. They also asked for the wavelengths. So let's finish that up. At this point, I find the easiest way to get wavelength is to go back to the idea that V equals F lambda. That's from the wave chapter. It is in your reference table, but it's from a while ago. Since I have the frequency, since I have the velocity, I can easily solve for the wavelength. What velocity am I talking about? How fast does red move? Speed of light, 3e8, yeah. So 3e8 over a frequency of 4.56 e14 hertz. And you'll be left with a wavelength of 6.58 e-7 meters. So you have successfully, for this hydrogen, found the wavelength and the frequency, starting all the way from the energy change, converting it, moving to frequency, moving to wavelength for today, physics.